Okay, good afternoon again, everyone. The next presentation, and I hand you over then to Joe Levy of CINEDIT in Switzerland, and he's going to talk about the weapon detection tool that he's using and creating in Impetus. So please, Joe.
Let me first thank you for allowing us to participate in this presentation. It is an honor. My name is actually Joaquin Levy, and I am one of the co-founders at CINEDIT. CINEDIT is part of the Impetus consortium, and we have one tool, which is the weapon detection tool as an intelligent video analytics tool. The weapon detection tool has a very clear mission, which is to detect weapons to prevent loss of life. For this, we have different approach, of course, using already installed CCTV cameras, but also trying to being able to overcome the challenge of data privacy that are confronted with us in regards to GDPR compliance. So our tool, as you can see on this image, detects weapons, but when it detects a weapon, what it does is it provides instant situational awareness. By that, it means that it shares in real time with the dispatcher a snapshot JPEG of the weapon, that is what the camera saw with the bounding box, as well as the GPS coordinates. Now, as you can see that even by using on our end the latest machine learning and AI algorithms, detecting a weapon using CCTV cameras, it's hard because the camera angle and the environment is never the same. You can take a camera that you have today in Oslo, you can take the same camera in Padova, the angle is going to be a little bit different, the environment is going to be different, such as lighting. Some countries can be very cloudy, snowy, rainy, like in Oslo, and sunny, like in Padova. So how do you technologically, the approach you have to have, like us, we work exclusively in infrared, meaning only with the night mode vision on, as you can see on the images below, except the image on the right, which was in the city of New York of a real shooting. So we all know that when weapons are not detected, it will lead to expensive site closure and loss of life, because the AI they use cannot be automatically calibrated when the camera angle changes. It is obvious that the person that you see on the bottom left, this policeman who responded at the Charlie Hebdo attack a few years ago, lacked terrible situational awareness. He had no clue as a first responder that his opponents were heavily armed and therefore he was outgunned. And that is what we call loss of life. So as a result, existing weapon detection system, they sadly produce false alerts because they do not have a top to bottom approach like CINEDIT has. So we have something unique, is that we learned that to detect a weapon, first of all, the artificial intelligence needs to be very accurate. But how do you keep accuracy? You need data in order to build better AIs. And working with smart cities requires data sharing. And this is a major hurdle for our consortium, I mean, for a company like ours, because it is a problem that due to GDPR compliance, it is very limited how the amount of data that we can receive between smart cities and high-tech companies like CINEDIT. And the problem number two that we have is called AI drifting. It means that an artificial intelligence becomes unstable. You see an AI is trained in a lab, in a closed environment, but as soon as you take out that AI and deploy it in another environment, the predictions will not be the same. You're not going to have like a confidence of maybe 96, 95%. It will drop down to 80%. And then you're going to have a lot of false alerts. For the brains in this session, here we show you a linear regression of what it means AI drifting. So of course, we're trying here to predict the target variable Y. And why I'm showing this? I'm showing you this because I need to show you like what this is, the seriousness of AI drifting. It is a very common issue, but it needs to be addressed in order to make the smart cities safer. So AI drifting means that in order to prevent it, the artificial intelligence needs to be retrained. It needs to receive more data in order to remain accurate. So when we update an artificial intelligence, when we receive more data to have a better weapon detector, it's the same way that when you use your phone and you do an update on one of the apps that you have. Now imagine if you'd be using the same app for the last 3 years without an update. Most probably you would not be using it because it would be simply outdated. And so by sharing data from partner cities, this can prevent drifting, and it keeps the weapon detection tool very, very accurate. And to do this, we need smart cities to provide sample data as an input to the artificial intelligence retraining process. But as you know, we have very strong GDPR regulations that are related to the sharing of data. You see on the screen here on the left, the person is actually entirely obfuscated in black. It means that we are not at all revealing any biometric data. We never record constantly. Our system only records when there's an alert. Yet it is very challenging to ask smart cities, can you send a person on the streets with a gun? We'd like to train our model. And this is one of the major challenges that we have been facing together, CINEDIT and the partner cities of the consortium of Impetus. However, once you bypass this, you can make the city safer. And actually, we had a breakthrough a few days ago when we did our acceptance pilot with the city of Padova, because we had this restraint of not being able to have the required data. So we decided to build synthetic data using 3D fake/real people. And by doing so, we are now very happy that we can still remain fully GDPR compliant. There's no bias in AI. Building a model that involves people holding guns, now we can produce, if you want to be clearly GDPR compliant, your data sets that you receive from the smart cities need to be 50% men, 50% woman. And in those male and female, you have to have an exact ratio of 50% white Caucasian and 50% color. And then you have to have dark skin color, light skin color, which was not possible before. But with the input of synthetic data from 3D images, and I'm talking about the same 3D images we use in high-end feature film, it is now possible. So there is no longer a bias idea towards the artificial intelligences that we're using in order to detect weapons. So with GDPR compliant, sharing of sample data, our AI can now help you remain safe and prevent terror attacks. I still need to point out that without a trained AI, unfortunately, the type of event that happened at the Bataclan in Paris is more likely it could happen to any one of us. So I would like to call on everyone to say, so what are you going to do about it? Meaning, are you ready to share data by keeping your GDPR compliance? Yes, of course. But do not hold back and do not close doors to artificial intelligences, because we are here to make you safer. Thank you very much. If you have any questions, I'd be happy to answer them.
So thank you very much, Joe. Okay, Joe, I have a question for you. When you said weapons, I think it's been implicit in what you say that you mean essentially pistols and rifles. If we were to try to extend this to be another kind of weapon, for example, knives, how dramatic a retraining would that be? Would that be starting from scratch, or would that be something that the same underlying technology could be trained to adapt to? Indeed, could you have one system that could detect both guns and knives in the same system?
In order to detect weapons, first of all, thank you for this question, Joe. To detect weapons, we today have multiple artificial intelligence. We're talking about small magazine-fed weapons. So small handgun, a small revolver. And if you can detect a small handgun, then you can obviously also detect AR-15 or an M16. That's part of our data set. That is what we can do today. Now, when we talk about weapons such as a knife is by nature much thinner object, and a knife will create what we call a lot of false alerts, false positives. So it calls for what we call pose estimation. The extrusion of the skeleton that you see on people would be like analyzing the movement and the behavior of passers-by. And this type of artificial intelligence is actually entirely different than just recognizing objects, such as small magazine-fed guns. Okay. So a knife, you would have to analyze this movement of someone reaching with a hand. Therefore, it is possible, and thank God we're using edge devices manufactured by NVIDIA, because we have the ability to throw on those edge devices that act as AI, that acts as little brains to turn CCTV cameras, to enable AI to CCTV cameras. We can now, in the future, it is possible to add knife detection, but it is an entirely type of cooking, I would say. Thank you.
Okay, thank you, Joe. I see that Matteo also has his hand up to ask a question.
Yeah, I was curious about your thanks for the presentation, first of all. I was curious about another aspect of training, and maybe relative to a less dramatic change. Say a city has a set of cameras and they are using the solution, and at some point they decide that it's time to change the hardware and to have new cameras with potentially slightly different. I assume that some of the recognition will still happen, but how much of an impact would that be? How much of a retraining would that require? And how much time would that require to basically be at the same level of performance as before? Or would there be any impact in a sense?
Thank you, Matteo, for this question. So today, when we train a model for the city of Oslo, we're taking a few thousand images only, but the camera is a fixed camera. Now, if that camera would move, or they would put that into another camera, what we do with the team of led by our CTO, Michael, he would need new data. And first, he would simply take a sample clip from this new camera and say, okay, let's just process that footage and let us just see how accurate the gun detector is. Now, if the gun detector is not accurate, it will need retraining. but it's going to be much faster than what we had, I would say, at the early stage of Impetus, because we have learned to build AI models with only a few thousand images. Therefore, retraining will happen here at our lab on site in about a day and a half. And so the constraint is just to have on-premises retraining and sharing at least a little bit of data so that we can also rebuild it in 3D. It's not yet automated, but we do hope that in the future, we're going to be able to automate this process. And again, a message from our CTO, there will never be a meta model that could detect any type of weapon using any type of camera angle. This is utopic. That is the reason why our system requires strict technical guideline. You can take any camera you want, but you have to respect the camera angle, the shutter speed, and as well make sure that you're using night mode vision on it. If not, it's going to be messy.
Okay. Thank you.
Thank you, Joe. Thank you, Matteo. Martina, had your hand up too?
Yeah, just a quick question, because in previous presentation we talked about the acceptance pilot, and as you also mentioned in your presentation, you had the possibility, or you were in any case obliged to do different tests in Oslo and then in Padova. So I would like to know if you can share with us some preliminary feedback from the operators, and also what was your experience in dealing with this kind of different tests?
So in Oslo, when we did the acceptance pilot in November, we prepared, and then the test was supposed to be in daytime, but we did it in nighttime. And we felt very confident because we use the night vision mode. So regardless of daylight, indoor or outdoor, the image quality is still very high. And so we send the dispatcher outside with their replica gun, and right away, the gun was detected for the first time at the SOC of Oslo. And I do very vividly remember one of the security officers putting out his cell phone at the SOC and calling his buddies at the Oslo airport from security, saying, hey, I'm seeing this weapon detection system and it works. That's outstanding. Now, that was great because we were on premises in Oslo. What we did in Padova had a completely different approach, different cameras. So we tried the model that we had, and they have multiple cameras. So we had the limitation of building what we call a small meta modem. Therefore, Liron, our junior data scientist, said, you know what, we cannot just wait like this and hope for more videos of people holding guns, because that ain't going to happen. So within a day and a half, we build a 3D character and we recreate the scene of what the camera would see in Padova. In 3D, it was all photoreal and fake and synthetic, put it this way. And we threw in a 3D character with a lot of guns, and we were able to complete the missing data with synthetic data. And of course, we were 3,000 kilometers away for the acceptance pilot of Padova. So we processed first a real stream from the hallway in the office that we shared the alert in real time at the SOC of Padova. Then we processed the real footage that was recorded in Padova, which was a person holding a real gun with real bullets. That person was a policewoman. But strangely, Impetus is calling for innovation. And doing demos, what we do, sometimes we use a messenger app so that we can share the alerts on the first responder's smart device. This is key. This is key. You don't want your first responder to be outgunned when he goes on site. So what did we do? We used Telegram Messenger with a bot for the acceptance pilot, and at our surprise, the people from the SOC of Padova were very happy to say, what is this tool? Hold on, I am getting an alert and I can share in real time the GPS coordinate, a JPEG, and a video shot of the alert with my first responders. Wow, that's amazing. So we were baffled because somewhere you have to be very much GDPR compliant, but on the other hand, you want to help save people. So those acceptance pilots were entirely different, but allowed us to rethink and see how we can reintegrate real-time alerting using innovative tools so that first responders have what we call, again, situational awareness so that they can feel safer when they respond. I hope Martina was able to answer your question.
Yeah. Thanks a lot.
Thanks indeed, Jonah. I think this thing of using the synthetic data opens a lot of possibilities for faster progress with many aspects of the work, I think. I think we have to close there because of the time, Joe. So thank you very much indeed.
Thank you for allowing us to present. Thank you.
You're very welcome, Joe. So now we can move on with the second last session of the day. And this is from Keren, Saint-Hilaire and Joaquin Garcia-Alfaro from Telecom SudParis, and they're going to talk about ontology-based attack graph enrichment. So I don't know which of the two of you are going to start, but please just go ahead.
Okay. Good afternoon, everyone. I am Keren Saint-Hilaire, and I will present you a cybersecurity solution proposed by me, Joaquin Garcia-Alfaro, Frédéric Stupens, and ENRICHMENT as part of the Impetus project. So we propose a ontology-based attack graph enrichment approach. This approach is based on logical attack graph. So to the next session, I will first talk about the motivation behind the approach and the background about graph and logical attack graph. Then I will talk about the approach and the implementation of the approach. And I will do a comparison between the related work and our approach. And then I will conclude. So an attack graph is a graphical representation of the path that an attacker can take to reach a goal. Generally, the attack graph are used by cybersecurity experts in order for them to make decisions about the remediation they have to take to mitigate attacks. But for the generation of attack graph, we require generally two types of information. There are information about the network and vulnerabilities information. The problem is that networks and vulnerabilities information are constantly changing. So in order for the attack graph to be completely faithful with the change of the system, we need to do a real-time monitoring of the network system. So we can confirm that an attack is successful. So this allows to do a mapping with the alerts from the monitored system. So we can move from a proactive attack graph to a reactive attack graph. First of all, a graph is a set of vertices and a set of edges or arcs. A directed graph consists of a non-empty set of vertices and a set of arcs that are formed by pairs of elements of vertices. So to be able to understand what is a logical attack graph, we need to know first what is an AND/OR graph. An AND/OR graph is a direct graph where each vertex is either an OR or an AND vertex. So a vertex represents an objective. So according to the type of vertex, this objective will need the conjunction or disjunction of the children of the vertex to, in order for the vertex to be fulfilled. So based on these three definitions, we can say that a logical attack graph is based on an AND/OR logical directed graph. So the nodes are logical facts that represent action that the attacker have to take in order to reach a goal, or the precondition that have been that need to be respected in order that this action can be taken by the attacker. And the arc represents the relationship between the nodes of the graph. So in order to validate our approach, we propose a use case scenario based on a smart city. So this scenario concerns a network. In this network, we have three computers. And the first computers that is the Alex computer represent the breach point. This is the computer where the attacker is located. And there is another computer, the Olivia computer, that is a vulnerable machine. On this machine, there exists the blue key vulnerability. That is a vulnerability that allows remote attacker to execute a code on the machine in order to remotely connect from a remote desktop protocol to the machine. So when the attacker connects to this machine, this vulnerability will give him the access to read the memory of this machine. So if the credentials of the user are saved on the memory of this machine, the attacker can then harvest the credential and reuse them. The problem is that the Fred machine and the Olivia machine have the same domain credentials. So the attacker can connect to Fred machine. That is a critical asset. This is a computer that contains a lot of sensitive information about the bus transportation of the city. So the attacker can then modify this information. This will lead to a mass of people on the buses, and this will cause panic and violence. So to validate the approach, as I said, we use a logical attack graph approach. So we need to use logic programming in order to validate the approach. So the first code explains that if an attacker A executes a code on the machine H, so the attacker will have access on this machine. So the execution of code on the machine is the precondition for the access to the machine. And then in order for the attacker to harvest the credential on the machine of the user U, the attacker have to previously execute the code on the machine, and the credentials of the user have to be saved on the memory of the machine H. So then by doing all this step of logical programming, this will allow the attack graph generation. So in order to enrich the attack graph, we will require the information from the monitored system. So a mapping is necessary between the information on the attack graph and the information coming from the monitored system. So the information in the attack graph will let you know that there exists a vulnerability X in this case, that we can say that this is the CVE 2002 on the machine H. And this vulnerability allows the attacker to execute code on the machine, that is the action. And this will lead to the impact of privilege escalation on the machine. And also in the attack graph, we can know that on this machine H, there is a user that is using this machine, the user U, and a project S that represents the Apache product is installed on the machine. So, and this the protocol that this project is used is the TCP protocol represented by the P, and A represent the port that each the 80 port. So we have all this information on the logical attack graph in terms of semantic information, and then we receive the information from the monitored system about the port and the protocol that is being used. So then the system will know that the attacker is trying to exploit this vulnerability. But to finish with the enrichment process, a vulnerability ontology is required. This will allow the system to know what are the other post conditions that can be exploited based on the exploitation of the vulnerability. So if a tweet exists on a vulnerable component of the monitored system, and then the algorithm has found some post conditions of the exploited vulnerability in the ontology, so new paths will be added on the attack graph. And in the case of our scenario, that is the panic and violence, the goal is to cause panic and violence on the bus. The system, the algorithm know that the reboot of the machine will not allow people to have access to the information about the bus transportation. So this can also cause panic and violence. So in this fact, an arc will be added between these two nodes, which will finish with the process of the enrichment of the attack graph for this time. So in order to validate the approach for the implementation, we use a reasoning engine that is based on logical programming. This tool is Mulval. It is an open source tool for attack graph generation. We also use the vulnerability description ontology of needs, and an integration of a prelude and elk stack, and we create a web interface for the attack graph visualization. So the logic programming allows users to go from the topological graph to the logical attack graph. A topological graph only contains the different connection between the different assets of the network, but it does give information about the action that the different action that the attacker will take in order to reach the goal. So this is the advantage by using a logical attack graph, because a logical attack graph show all the paths that the attacker can take. The actions in the logical attack graph are represented by the node in green. So in this case, we see that there is a lot of action that the attacker have to take in practice in order to exploit, to reach the goal. And the vulnerability represented by red node in this case. Also, an advantage with the logical attack graph is that a logical attack graph have a lot of inferences abilities, because it is a semantical approach. The logical attack graph contains all the semantical information about the attack graph, so it is really more easy to do the mapping between the proactive graph and the information coming from the monitored system, in this case, the alerts, the logs, and the information from the vulnerability description ontologies. And then it is very more simple to do the enrichment of the graph and to go to the logical reactive attack graph. So a lot of approaches about attack graph generation exist in the literature, but there are some limitations. For example, there exists an approach about the attack graph generation based on logical programming and use of a SIM in order to monitor the system and to do a correlation. But the problem with this approach is that for the proactive attack graph, they did not take into account the state of the network. They only use the information about the vulnerabilities. And there also exist approaches that are based on planning programming. In this case, they don't do enrichment of the attack graph based on the change of the network. So this will not really help the cybersecurity expert, because they will have each time to generate the graph. And there also exist approaches that use ontology for the attack graph generation, but more of the approaches just use the ontology in order to enrich the ontology, a cybersecurity ontology with information from an attack graph. So it's the same problem. There is no real-time monitoring on the system. And then there also exists other approach where they are updating the graph based on ontology, but the cybersecurity experts have to enrich the ontology with the data of the network. So it is not a work that is being doing automatically. So in terms of efficiency, it's not really efficient for the cybersecurity expert. So to conclude, in this approach, we take into account the real-time update of the system, and the evidence of the semantic information of the logical attack graph is really helpful for doing the inferences and enrich the attack graph in a real-time process. So if you have any question, I will take them for the moment. Thank you for your attention.
Thank you very much indeed, Keren. Okay, Keren, I have a question. At the very beginning, you explained this is about networks, then you talked about ontologies. Something you didn't really mention though is how big the networks could be, how many nodes there would be in a network. And when you apply these techniques, are there scalability issues as the number of items in the network increases? And have you tested it on what sizes of networks?
Okay. Yes, in fact, the problem with the scalability of the network has been addressed in other research. So in this case, in order to avoid this problem, for the Impetus project, as we are doing the integration with another partner, XM Cyber. So the idea is like to just take only, the network is big, but there is a segmentation. So for the attack graph generation, we will just take the component that are relevant for one scenario. So for each scenario, we have a big network, but not all the machine can attack all the machine in the network. So it is kind of a solution to this is to do the segmentation. So by using like we have just to group them by the asset that can be a critical asset based on one other machine. For example, the Alex machine in the very beginning. I will go back. Okay, for example, an attacker that is located on the Alex machine, for example, can allow, if it affects the Fred machine, it can allow affect, for example, 20 machines on the network. So in this case, we separate this by scenario, and we will not have the problem of scalability by the edge of the network. I don't know if I answer your question.
I think so. If I understood correctly, you segment the network to the key machines of interest in a particular scenario. It wouldn't be feasible to involve every computer in a big network. The scalability would then be a problem, if I understand.
Yes, what I maybe did not explain well is that the possibility to have access to all the machine still exists, but we have to select which machine we want to, for which machine we want to see like the vulnerabilities. For example, the blue chip vulnerability from Olivia will cause impact on maybe 10 machines. So if we select the machine of Olivia, we will see the attack graph for this 10 machine in the network. And if we select the machine of Fred, for example, maybe it's only concerned 20 machine.
Okay. Thank you, Karen. We have a more fundamental question from Tom Robertson in the chat. And he asks, please explain how attack graphs are used in Impetus. Are they displayed to cyber experts? Are they used to initiate defense?
Yes, so for this moment, we are just we already test the attack graph generation and enrichment on the acceptance pilot. So the goal in this paper, we only talk about the attack graph enrichment, but the final goal is not to just stay on the attack graph enrichment, but also to propose optimal remediation based on the attack graph generation and enrichment. So in one paper, we cannot talk about all the solution in one paper. So I think it's the problem. So I don't know if I answer, but in fact it's the final solution will be for defense, like in order for the cybersecurity expert to know, okay, which remediation I have to apply in order to avoid this attack, or to take some measure to repair the problem I have because they already reached the attack on my network.
Okay, I think you did answer Tom's question because fundamentally, indeed, it's for defense that this is all about, and you're looking at a particular dimension of reaching there, I think. I think we need to move on with respect to the time. So I think we say thank you very much, Keren, and we move on now to the last session of today, and that will be presented by Paolo Mocellin from University of Padova. And the title is An Approach to a Safe Egress from Public Spaces Driven by Risk Principles. So please, Paolo.
So hi everyone, my name is Paolo Mocellin and I am a researcher at the Department of Industrial Engineering of the Italian University of Padova. Today I want to share with you our research activity dealing with an approach to a safe egress from public spaces driven by risk principle. This work is carried out within and thanks to the Impetus Horizon 2020 project funded by the European Commission under a research and innovation program. Besides me, Matteo Bottin, Chiara Vianello, Giulio Rosati, and Giuseppe Maschio are contributing to this research with different roles. This research moves from the Impetus Horizon 2020 project. It aims at integrating interdependent solutions and concerns approaching three pillars: technologies, processes, and ethics, to improve the security of public spaces, smart cities, assisting law enforcement, and end users in responding to complex events. One of the tools that is being developed in the project is at suggesting and assisting end users in optimizing the response to scenarios triggered by an event. This approach can work together with smart city sensors and actuators, for example, with people counting sensors, to help to respond to critical events, facilitating coordination and the dispatch of required resources as efficiently as possible. Just a few words on the university to which we belong. The University of Padova is one of the oldest and most prestigious systems in Europe. It was founded in the 1222. This year is 800 years old. It is linked to many famous names, including Copernicus, Vesalius, Galileo, and William Harvey. Padua University has been a pioneer of several endeavors, with the first university botanical garden in the world, now UNESCO World Heritage Site, and the first permanent anatomic theater inaugurated in 1678, which is here represented. Currently, it has more than 60,000 students and more than 100 bachelor and master degree programs incardinated in 32 departments. The University of Padova within Impetus project represents an academic partner for research activities that are carried out by two research groups with different expertise. The first is headed by Professor Giuseppe Maschio and the other by Professor Giulio Rosati. Our contribution to the project is expected to make available to the consortium scientific knowledge on crucial aspects, including the management of crowds, but also to model peculiar features of the two pilot cities involving the project, Padova and Oslo in Norway, in relation to physical configuration of open public spaces, emergency routes and distribution, and people flow. So why an approach to people egress from open public spaces? This question is topical since we usually hear about crowds, management of public spaces, emergency plans for railway stations, airports, and so on. In fact, a critical triggering event may induce or require the egress of people simultaneously. Think, for example, to a terroristic attack targeting a vulnerable public space, or more frequently, planned events that require the egress of a large number of people. For each of these, the topic of egress management emerges. Crowd forces can reach levels that are almost impossible to resist or control when escalating. Unfortunately, deadly crowd surges have occurred for decades. This means that people can die or be injured during a critical egress. In other words, a poor crowd management can lead to side effects. Critical is the crowd control versus the crowd management, in the sense that an approach to such situations should include a process that considers all human behavior in crowds. In this framework, the so-called crowd science can and should assist law enforcement and support end users when managing complex events that may originate from triggering events and that ask for a crowd management under different boundary conditions. We can say that the crowd science refers to the scientific approach to crowds. In fact, crowds behave according to some rules that can be approached systematically. through models that embed physical constraints, geometry, and human behavior during evacuations. The science, therefore, relies on the scientific approach to study the flow of crowds in different situations, including normal and anomalous scenarios. It may help in designing and optimizing public spaces oriented at handling a large number of people simultaneously and safely. In addition, simulations and models can give valuable information for a planning step, including egress timings and critical people density associated to operate criteria. On this line, simulating people egress from an open public space can be used to recreate reference scenarios, which can be spent in different ways. Firstly, to support emergency operators in planning and managing evacuations. Then to predict the human behavior and parameters related to the egress according to different boundary conditions. Finally, related considerations can support the optimization of the response to a critical event, enhancing, let's say, the resilience against the side effects related to crowds triggered by threats. Modeling an egress scenario involves different parameters that require a proper quantification. One of the most challenging is the human behavior in crowds. Typically, we are asked to answer the questions like, does the crowd experience panic or rationality? Or people in the crowd do show altruism or egoism? The overall crowd behavior is determined according different factors, including cognitive aspects linked to expectations, knowledge of a specific context and attitudes, but also by environmental factors, including social rules and influence among people. Finally, behavior of the component of a crowd is sensitive to behavioral factors like social skills and familiarity. In a general perspective, the results of a crowd movement can be quantified in terms of flow rate of people, that is the number of people circulating per unit of time with respect to a location. Space, direction, and time determine how a group of people moves inside a public space. The complexity is also enhanced by the possibility of different triggering events at the pace of the crowd behavior. Crowds may circulate according to the degree and detail of information and knowledge collected by people, but also depending on operative strategies imposed during an egress scenario. The latter, different from the previous parameters, is intended as an external constraint held by emergency actors that can induce specific responses by the crowd. Simulation tools based on validated parameters can assist in dealing with such a complexity on egress dynamics. We propose an approach based on the rationale that is shown in this slide. The aim is supporting decisions and response by law enforcement and the end users, optimizing the management of large groups of people. Based on selected geometry, pedestrian behavior, and configuration of escape routes, the egress is first simulated according to some reference scenarios that can be discussed with the stakeholders. Such scenarios are compared with data retrieved by sensors, for example, counter-person sensors that allow defining the real context in terms of numerosity and people distribution. On this basis, the framework can be ranked in terms of risk in order to set the rules of management of actions, therefore suggesting proper guidelines during decision and response. The approach can take advantage of two inputs, as indicated in this chart. On one side, the simulation of egress is performed on specific finite cases with a view on the entire domain of the public space considered. This step is performed offline in the sense that simulations are run in a planning step that comes before an event occurrence. On the other side, information gathered from the simulation of scenarios can take advantage of smart city infrastructures. In fact, sensors and actuators can make available real-time and online data that allow for the matching with a pre-simulated scenario and the related features, operating guidelines and actions taken. The risk assessment step follows these procedures and makes it possible to indicate how a risk index spreads along the open public space. Without going into much detail, The model for risk analysis is based on the so-called radial basis function. They are determined by based functions that embed the distance from the sensor and weights that are assigned according to anomalies detected by sensors with respect to the base case simulated. In this way, we can map in space and time a risk index after a triggering event has set in motion the crowd. Let's see this approach through a case study. We consider the public open space here represented, and we need as an input the geometry of the space. Normally, in this case study, 6 egress routes are available as indicated and numbered. According to the event, different number and classes of people can be featured, and as said, this parameter has a role in the overall egress efficiency. In addition, a set of operating rules during planned or unplanned events can be expected depending on the specific context and decisions imposed by authorities. On this basis, we simulated a set of egress scenarios under different constraints. We discuss here only 2 of these scenarios, of which the risk index is assessed. However, related concepts have a large degree of flexibility in simulating different events. You can see here a first simulated scenario involving 1,000 people. The features of the people are allocated according to statistical distribution, but there is a large opportunity to set a range of parameters related to age, velocity, and behavioral properties of each person. In this scenario, all egress routes are available for evacuation. Let's see how the crowd behaves after a triggering event. As you can notice, a significant number of people prefer the egress routes number 6. These egress routes, along with the egress routes number 5, experience a phase of overcrowding during evacuation that in a base case scenarios lasts for about 40 seconds. On the contrary, egress routes numbered as 1, 2, and 3 are underused with respect to their capacity. It is clear how people in crowds tend to aggregate to familiar queues despite a discouraging waiting time for egress. These logics can be approached in this strategy. A different egress can be induced, for example, by using actuators or proper management strategies. These scenarios show how the crowd would behave when 3 out of 6 egress routes are made unavailable. We should consider that once properly planned and managed, such a context may leave space to a corridor to emergency operators coming to this area. In the present case, the corridor groups entrances are previously identified as 1, 5, and 6. Let's watch at the simulation. We can observe that despite a longer total time for egress, a similar context results in a limited overcrowding on egress route number 2 that, according to people density maps, never exceeds a critical threshold. Egress route number 3 is still underused, but the egress capacity of all the egress routes is better balanced and optimized. For example, in the smart city concept, the selection of the egress route can be induced by smart lighting once a threat is detected. In this approach and context, the simulation gives valuable information on what is happening across the egress routes. These figures show a comparison between the flow rate of people that goes through an egress gate in time coordinate according to the 2 simulated scenarios. The maximum flow rate of people crossing a gate can be estimated along with how this information varies in time, especially in the very first moments after the triggering event. This allows also for setting a threshold value that alerts about an ongoing anomalous scenario. During the egress, different trends can be detached, and these simulated profiles can be compared with data retrieved, for example, by counter-person sensors. Deviation with respect to a baseline can be used as an indicator or alert of an ongoing event that requires an immediate management. Starting from these discussed scenarios, a risk index is evaluated. The related magnitude and variation in space and time can be interpreted as a driver for tracking how a context behaves before, during, and after a triggering event. For example, we associate a risk index map to the first scenario with all egress routes available before a perturbation occurs. The location of egress routes are indicated, in which a base case value is expected. If we focus to a later time frame, for example, after 12 seconds, the risk index is distributed according to this map with perturbations tracked at the egress gates. The risk index clearly grows with alterations in egress dynamics. The same happens with the second scenario, although a different risk index trend can be observed. In this case, after 12 seconds, the highest risk index is observed in the right corner, corresponding to the specific egress route number 4 in our simulations. This approach allows also detecting anomalies. For example, given the first base case scenario, free from anomalous people flows, that is scenario A in our work, a sensor located in the location indicated on the right can detect an anomaly based on people flow criteria after 12 seconds, a triggering event has occurred. Some consideration and comments can be formulated. As said, some scenarios of crowd movement can be intrinsically at high risk, requiring proper planning and a response. A risk increase can be, let's say, ascribed to the total number of people present within a certain area that a triggering event induces egress. Also, the availability and the vulnerability of egress routes may impact their overall performance. It is clear that the nature of the triggering event induces a crowd response. Some triggering events, including explosions or fires, can lead to unavailability of planned egress routes and therefore to more severe outcomes. We have shown that the crowd management is a valuable strategy to mitigate such scenarios, which can be simulated in advance. This can be accomplished by properly planning, let's say, and driving an egress through a set of egress gates to relieve overcrowding. At the same time, such a driving approach can help decision makers to allocate emergency corridors in order to optimize resources based on a risk-based decision approach. In this strategy, simulations can help assess a risk index that can be associated to time for alerting about the critical situations that emerge in terms of an anomalous people flow. Threshold values can be simulated and identified according to criteria that the law enforcement bodies want to achieve, also in light of the vulnerability of a specific context considered. I want to conclude my presentation with some insights on egress from public places. Evidently, some misconceptions about panicky crowds exist. Despite being characterized by different parameters, a crowd behaves according to some rules that can be approached from a scientific perspective. In this light, crowd science and simulation, as those illustrated in this work, can support law enforcement in planning and managing criticalities related to planned but also unplanned events. Once a risk-based approach is adopted, reference scenarios can be used to alert about threshold values that help in correctly adopting a resilient response to a triggering event. In addition, a structured approach to egress scenarios can help assessing the performance of the public space in light of selected threats and operational solutions. But it must be said that one of the most important challenges is coupling such simulations to real-time data from sensors that can be used to give an indication of the related risk. This indicator can be strategically linked to a set of operational guidelines that enhance the management of actions and resources for responding to such events. I stop here my presentation and I thank you very much.
Thank you very much indeed, Paolo. Does anyone have questions for Paolo? Martina, please.
Yeah, thank you, Paolo. Very interesting presentation, and also we have seen in this conference a lot of different tools that with different maturity level and they deal also with different end users. In your last slide, you were showing the possibility of using also this tool for different events, for different phases of the events, like for being ready, and then after the events for learning. So I would like to, if you can provide some additional information on how the tool has been used in these projects, and also what are the main challenges for this tool in this kind of projects. Thank you.
Yeah, thank you very much for your question. Yes, this approach can be used in different situations. Within the Horizon 2020 project Impetus, we have taken, let's say, the occasion to validate some of our approaches to such a situation in the pilots planned in Oslo and Padova, during which we have also, as a consortium, simulated different initiating events, a gunshot, a struggle, or we can embed different initiating events because of a sort of flexibility in this approach to manage, let's say, in a general perspective, a triggering event. A triggering event may be represented not only by a person that is doing something, but also by a natural event like an earthquake or something that is severe in such a way to put people in a situation to go away from a specific place. But also in the case of explosions or fires or toxic attacks, these are also very important and very interesting initiating events that can be embedded in such an approach. I hope to have answers to your question.
Yeah. Thank you so much. And then just another quick, that is more a curiosity than a question. I assumed that the square and the image that you shown was Piazza dei Signori, right?
Yeah, it was Piazza dei Signori.
This is what we learned during Impetus, but probably for ethics issues you didn't mention the name, so now we know where we did the test. I was wondering, because I imagine that for this kind of models, most of the time and effort is spending in modeling the different places. So how much approximately you required to model with this kind of details a square, and also the squares that you modeled for the two acceptance pilots?
Yeah, as you have said, it is a matter of time in planning and performing the numerical simulations. It lasts about some days to proper set the simulation that then should be validated with some parameters that, for example, need a sort of correction. Running simulation is very short. It requires a very short time period, let's say some minutes, but arranging the simulations, it depends on the degree of detail that we want. It requires even hours. So this is my answer to your question. Yeah.
Thanks a lot.
Thank you, Paolo. I have one question. You mentioned briefly at one point that where this could lead to was using smart lighting to perhaps, if I understood right, to indicate to people what might be the advised egress route. Do you know of any research that tells the extent to which people would actually follow the advice? So if there's a green light saying you should be going this way, but the people think, I think that way looks better, you know, it looks more open or whatever. Is there any research about that? How obedient are people in following advice?
Yeah,
I know that the people in this project aren't very obedient, so I just I just wonder if there's research.
Yeah, there are some research work oriented at analyzing how people react to a smart lighting, to a light, to colors, and so on. And what it emerged is that sometimes the smart lighting, it is not enough to drive people out of a public space. Usually a strategy that is more effective is saying something loudly with an indication from the city infrastructure that is saying, okay, people, please take that way that is green lighting. So this is what is emerging from the research activities. Yeah.
Okay, thank you very much. Just when you connect with that, I remember reading some research about fire alarms for children, and adults, they evacuate if they hear a bleeping noise. Children evacuate if they hear a voice of an adult saying, "There's a fire, you should leave." They're more receptive to that.
Yeah.
Anyway, I think we've got to the end of the day, and so thank you very much, Paolo.
Thank you.
And indeed, thank you to all of the presenters today who've all given very interesting presentations in a lot of detail on many interesting topics. I would like to open now for anyone who has any final questions or indeed observations that they might want to make in conclusion about where did we get today. Does anyone have anything they would like to say? Either the people who can speak or the people who can write in chat. Anything you want to end with? Okay, then I can say what I would think, for me at least, were the conclusions from today. People can challenge or agree or disagree with me. The day started with a discussion about, is Impetus challenging or not? Matteo told us that he thought it was challenging when he started to write it, and even more challenging when the project started to run. And when I sit here today and listen to all the presentations and all the details and all the complexities of the various parts, I'm starting to think it's even more complicated than it was this morning when I joined the meeting. There's really a lot going on here. I learned that the word resilience is something that we haven't talked about on a day-to-day basis very much in the project. But from some of the context that I got today, I understand more that actually fundamentally at the core of what we're doing is an attempt to improve resilience. And I hadn't been very conscious of that before. I think that our idea of the 3 pillars, which is something we've built a lot of the project structure on, of technology, ethics, and process, is indeed a sound and well-founded way to go. I think that's been confirmed in various ways by what was presented today. And I think that it's also clear from what we've heard today that all of the theories, all of the technology, all of the ideas wouldn't get very far if it weren't for the validation that we're doing in these 2 cities. And my final conclusion for the day is that I'm a lucky guy to have such a good team working on such an exciting project. And I think I'll make that be my last word for today. I don't know, Harald, if you're still here, if you want to say goodbye or anything.
Yes, I will. Thank you, Joe, for the excellent sharing. And everybody kept time and they showed up. And this was quite a lot of information. All speakers, thank to them, thank to the visitors. And I think what we have here recorded, that will also be used in the publication material we are providing for Impetus. So thank you, Joe and the team and all your listeners. The only thing I can say, you're welcome back tomorrow, 10 o'clock, to the last day of the conference. So thank you all and have a nice evening.
And same to you, Harold, and thank you once again on our behalf for giving us the opportunity.
Thank you.
Goodbye.